You ever wonder what keeps the entire internet from just falling apart? Well, there are these invisible rules working in the background, and one of the most important is something called subnetting. It's kind of the unsung hero of network organization, and today we are going to pull back the curtain and see exactly how it works. So let's start with the big question, right? You've got billions of devices. Phones, laptops, servers, even smart refrigerators, all needing their own unique address online. How does the system handle all that without just grinding to a halt and running out of space? To put that in perspective, this is the number we're dealing with. The Internet's original address system, IPv4, had a cap of about 4.3 billion addresses. Now, back when it was created, that sounded like an impossibly huge number. Today, it's not even close to enough. So this scarcity created a huge problem that needed a really clever solution. And here's how we're going to figure it all out. First, we'll look at the address problem itself. Then, we'll see why subnetting is the perfect answer. We'll check out the tools you need to do it, compare the different strategies, and then, finally, we'll walk through a real-world example to make it all click. Okay, first up, the Internet's address problem. And the subtitle here really says it all. You've got a limited, finite number of addresses for what feels like an infinite demand. So the original solution was to create these rigid classes of networks. If you were a huge company, you might get a Class A network, which gave you space for over 16 million devices. I mean, way too big for almost anyone. But a smaller company might get a Class C, which only had about 254 addresses, and that was often too small. It was a one-size-fits-none system that ended up wasting millions and millions of precious IP addresses. And that wastefulness brings us to our next section, and the truly elegant solution to this whole mess, subnetting. This is where people got smart and figured out how to divide and conquer the address blocks they were assigned.
So what is it exactly? Well, at its core, subnetting is just a strategy. It's the act of taking one big network and chopping it up into multiple smaller, more manageable subnetworks.
I love this analogy because it makes it so clear. Imagine you're given a giant barrel with 100 apples. It's a bit chaotic. Subnetting is like taking those 100 apples and neatly organizing them into 10 smaller barrels with 10 apples each. You still have the same number of apples, but now they're partitioned in a way that's way more useful and organized. And the payoff for doing this is huge. By creating these smaller groups, you cut down on unnecessary network chatter, which makes everything run faster. It makes the whole network easier to manage. And of course, the big one, it lets you use your IP addresses way more efficiently. As a bonus, it even boosts your security, since you can isolate these different subnetworks from each other. Okay, so how do we actually do this? Let's get into the subnetting toolkit. Don't worry, we're going to break down the key concepts and formulas you need, and it's simpler than you might think. All right, the whole magic trick of subnetting comes down to this one core idea: borrowing bits. Every IP address has two parts, a part that identifies the network and a part that identifies the specific device or host on that network. Subnetting is literally just redrawing the line between those two parts. You borrow a few bits from the host side and give them to the network side. So how do you tell all the devices on your network where that new line is? You use something called a subnet mask. You can think of it like a stencil or a template that you lay on top of an IP address. It's the tool that tells every single device which part of the address is its network name and which part is its own unique name. It defines the boundaries of all your new little subnets. And that leads to our first really simple formula. The number of new subnets you can create is just 2 to the power of n, where n is the number of bits you decided to borrow. So if you borrow 1 bit, you get 2 subnets. Borrow 2 bits, you get 4. 3 bits gets you 8, and it just keeps doubling. Pretty straightforward, right? But of course, there's a trade-off. For every bit you borrow to make more networks, you have 1 less bit for your devices. So the formula for how many hosts you can have is 2 to the power of n, where n is the number of remaining host bits minus 2. Now, why minus 2? Well, every single subnet needs to reserve 2 addresses, one to name the network itself and another one to broadcast messages to everyone on that subnet. Okay, so we've got the tools. Now let's talk strategy. We're going to compare the 2 main ways to approach this, the old one-size-fits-all method versus a much smarter custom-fit approach. And this comparison just lays it all out perfectly. On the left, you've got FLSM, Fixed-Length Subnet Masking.
This is the simple way. Every single subnet you create is the exact same size, but this can be super wasteful. On the right, you have the much more advanced method, VLSM, Variable Length Subnet Masking. This is the game changer. It lets you create subnets of different sizes, so each one can be tailor-made for what it needs. It takes more planning, but it is incredibly efficient.
So that brings us to our final section, putting subnetting to work. All this theory is great, but let's apply it to a practical, real-world problem and see exactly why VLSM is so powerful. So here's our challenge. We have a company that's been given a single block of 254 usable addresses. They need to divide it up for 3 departments with very different needs. The IT department needs 100 addresses, sales needs 60, and management needs 34. The process for solving this with VLSM is super logical. First, you always sort your needs from largest to smallest. You have to tackle the biggest requirement first. So in this case, the IT department. You figure out the perfect size subnet for them, and you assign it. Then, you just move on to the next available address, and you repeat the process for the next biggest department, sales, and so on, until everyone has their own custom-fit network. And here it is, the final result. It's beautiful. Look at this. The IT department gets what's called a /25 network, which gives them 126 usable addresses, perfect for their 100 computers with room to grow. Then sales and management each get smaller /26 networks, giving them 62 addresses apiece, which is again a perfect fit for their needs. It's an absolutely elegant solution with almost 0 wasted addresses. And that's really the key takeaway here. VLSM is about more than just saving addresses. It's about smart, intelligent network design. It lets you be incredibly efficient with a resource that's becoming more and more scarce every day. So when you look back, we've seen how subnetting took the potential chaos of a limited address space and brought a logical, scalable order to it. It's one of those foundational, invisible rules that just makes our digital world work. And that leaves me with one final thought for you. What other invisible rules are out there quietly keeping our online world running smoothly every single day?